Standard thermodynamic heating relies on thermal transfer. You apply kinetic energy from a hot element to a cooler object through direct conduction, or you use Joule heating, relying on the electrical resistance of materials like nichrome wire to generate ambient heat. A microwave oven contains no heating elements. It bypasses thermal conduction entirely. Instead, it uses high-frequency electromagnetic fields to directly induce kinetic energy at the sub-nanometer molecular level. To understand this process, we have to look at the physics from the ground up, starting with the geometry of a single water molecule and scaling up to the orbital mechanics of the vacuum tube powering the system. This appliance is an electromagnetic kinetic inducer designed to operate on a microscopic scale. This 3D diagram isolates a single water molecule, H2O. It has a specific folded V shape, with the oxygen atom positioned at the center vertex. This geometry forces the electrical charge to be biased, creating a slight negative zone at the oxygen atom and positive zones at the hydrogen tips. This asymmetrical charge distribution creates an electric dipole. The core mechanic of dielectric heating relies on this dipole. When an external electric field is applied, the water molecule physically rotates to align its internal charge with the polarity of that field. If you alternate the polarity of that external field exactly 2.4 billion times per second, a frequency of 2.4 gigahertz, the water molecule violently flips and vibrates in place, struggling to keep up with the changing current. This continuous, violent rotation translates directly into internal molecular friction. The friction generates rapid, highly localized heat. Because this method targets specific geometric dipoles, it is strictly dependent on moisture. Without water molecules to manipulate, dielectric heating loses its efficiency, which is why dry foods remain cold in a high-frequency field. This precision targeting also creates physical hazards. If you heat structures with high water content, like intact eggs or sausages, the rapid internal dielectric heating converts the targeted moisture into steam. The trapped water vapor expands outward until the biological membrane or shell ruptures under the internal pressure. Dielectric heating successfully exploits the microscopic geometry of water. The engineering challenge is generating a continuous 2.4 gigahertz alternating field inside a commercial kitchen appliance. The solution to generating that precise frequency was the magnetron, a technology originally developed in the 1930s for British and American anti-aircraft radar. Detecting enemy planes required short-wavelength radio waves capable of reflecting off metallic holes. This animated cross-section shows the internal geometry of a magnetron, a specialized bipolar vacuum tube. At its center is a heated cylindrical cathode, which boils off electrons. These negatively charged particles naturally attempt to travel outward in a straight line toward the positively charged circular anode block, which contains hollow slotted cavities. To manipulate this flow, permanent magnets are positioned above and below the vacuum tube, driving an external magnetic field straight down, perpendicular to the electron's outward path. This setup relies on the Lorentz force, a physical law stating that any moving electric charge passing through a magnetic field will experience a perpendicular force, physically bending its trajectory. Because of the Lorentz force, the electrons never reach the anode in a straight line. Instead, they are pushed into a tight, rapidly spinning, multi-spoked orbit around the central cathode. As these rotating spokes of electrons brush past the hollow cavities cut into the anode block, they induce a resonant oscillation. It is the same aerodynamic principle as blowing air horizontally over the open neck of a glass bottle. The physical dimensions of these cavities dictate the resonance. They are mathematically tuned to oscillate at exactly 2.4 gigahertz, generating electromagnetic energy that is then extracted from the tube via an antenna. The magnetron uses the Lorentz force to manipulate the orbital mechanics of electrons, translating a straight electrical current into high-frequency microwaves. Once extracted by the antenna, those 2.4 gigahertz waves are blasted directly into the primary cooking chamber. The interior of the chamber is lined with specialized metals like stainless steel. High-frequency radio waves cannot penetrate dense conductive surfaces. Instead, they reflect off them with high efficiency. These continuous internal reflections create a chaotic web of overlapping electromagnetic waves. This ensures the waves penetrate the food from multiple angles simultaneously, achieving volumetric dielectric heating. This highly reflective box is a Faraday cage. It serves as an absolute barrier, blocking internal electric fields from leaking into the surrounding environment. This side-by-side wavelength comparison shows exactly why that shielding is necessary. The 2.4 GHz output of a microwave perfectly overlaps with the frequency band used by standard IEEE 802.11 Wi-Fi routers. Without a heavy metallic Faraday cage, activating a microwave would flood the immediate area with brute force signal interference, instantly drowning out and disconnecting local wireless data networks. The ubiquitous metal box of the microwave is a functional electromagnetic quarantine zone, mandated to keep the local radio spectrum intact. The first commercial microwaves built using this radar technology were massive, expensive machines, limited to commercial use by the heavy materials required to build early magnetrons. In the 1970s, Japanese manufacturing innovations replaced expensive Alnico magnets with highly efficient ferrite magnets. This reduced magnetron size and cost, allowing the microwave to become a standard kitchen appliance. The core principle of dielectric heating extends well beyond consumer appliances. It acts on any material containing trapped moisture. In the commercial lumber industry, massive dielectric heating arrays press thick square timbers between parallel electrons. The high-frequency field dries the wood and cures specialized plywood adhesives uniformly from the inside out. It is even utilized in traditional woodcraft, like nagewappa. By applying dielectric heating to raw cedar, craftsmen generate high-temperature steam entirely inside the wood grain, making thick cuts pliable enough to bend without snapping. The physical process scales from anti-aircraft warfare to the specific electric dipole of a single water molecule, heating consumer meals and curing industrial timber. The microwave oven applies the physics of resonant cavities and Lorentz forces to moisture, turning high-frequency vacuum tube engineering into a standard kitchen utility.